All right. In this last module on failure, I want to bring in a new type of failure mode that we can sometimes see and look at ways to resist that as well. And so that is the concept of creep and then resistance to creep that we want to talk about. All right. So, creep, along with having a really bad name for a type of failure, is deformation that occurs at elevated temperatures, but also static loading. So, we just got done talking about cyclic loading or cyclic loading. So, this is going to be static loading, typically very low levels, but at elevated temperatures. And so this brings with it um, time dependency of deformation and also plastic deformation of materials. And um, again, it's a constant load or stress that's applied, and it's typically done at levels that are over zero point 0.4 of the melting temperature of that material. So obviously, most things that we talk about at room temperature aren't subjected to this. There are exceptions, obviously, to that if they have very low melting temperatures. But for us and kind of the design, if we're talking about design of parts and so forth, this would obviously be for applications where there's a high temperature. So that might be at power plants where the heat goes up, in turbines where it can be subjected to significant heat, things of that nature. Anything in the furnace obviously is subjected to those types of issues. And so, excuse me. And so we typically look at again, it's steady state, and we look at a what we call a creep rate. And so you can see here we're using epsilon, which is strain, and so it's S for static, and then the dot above all in engineering always refers to a rate. So it's strain rate is essentially what this is. So steady state strain rate. And so that's the change in strain with time. And so we basically, under that applied constant load or stress at the given temperature, we can look at the creep strain epsilon as a function of time. And so this is kind of a typical curve that we might see. And so initially, as always, there's going to be an instantaneous deformations, right? So this is the kind of gap above zero that we see initially. And then we kind of refer to three different three different time periods: primary, secondary, and tertiary before we have rupture. And the slope here is referring to that steady state creep rate. And again, this is most commonly tested at constant loads and then elevated temperatures. So, so that's kind of creep in a nutshell. We haven't talked about it a lot, but I just wanted to kind of introduce the topic. But more importantly, we can talk about resistance to creep. Because these strategies tend to be a little bit different than other kind of techniques we've talked about so far, because creep at this high temperature is a different type of failure than what we've seen. It's a more long-term effect, right? There's a lot of time and strain involved before failure. So the number one thing would obviously be to pick a material with a higher melting point, because then we would be at a lower relative temperature to its melting, right? So that's number one. So that's a way we can resist creep materials. So the materials that you tend to see in those applications would tend to be on the higher side of melting temperature. So you can see here that mercury and aluminum are relatively low melting temperatures, whereas silver, it's a little higher, and then tungsten, you can see, is much higher melting temperature. And so that's one way. Things like nickel as well have a relatively high temperature, and so those are ones that you would want to pick for these applications. Additionally, you want to look for high elastic modulus materials. So far, when we talked about resistance to plastic deformation, we're looking at yield strength or even tensile strength. But here, for creep resistance, you want to look at more what we call rigid materials generally, but those are ones with high modulus. And so if we kind of look at these materials here, you'll notice that tungsten, again, it's very rigid on top of having a really high melting temperature. So those are the types of materials that we're looking for. And lastly, this is something that counters what we've talked about in a number of other strength applications. But instead of picking something with very small grain size, which are typically very strong materials, we actually want to go with something that has either very large grains or, in fact, has no grains. So it's single crystal. And so let's kind of go over this in more detail, because this is the one which kind of counters what you might expect based on what we've talked about with strength. So we want these larger grains to effectively limit the amount of grain boundary sliding that we can occur. So at these very high temperatures, the grains can move relative to each other much more easily, because again, it's at a much higher temperature and plastic deformation can occur much more rapidly. So eliminating those grains or making them larger, or sometimes changing the shape, making them more columnar. So think of column, so they're kind of oriented in a certain direction, which is what you have here. So this is kind of shown the traditional conventional casting, and you can kind of see all these little spots. Those are small grains. This is columnar, where the grains, you can see a very few grains, but they're all arranged on the vertical axis. And then here's a single crystal of that. So obviously this is going to be the most expensive, because single crystals are very hard to grow. Things tend to want to be polycrystalline. And then this is going to take some work. So this does require additional energy to do those, or additional funds, to make this happen. But that can improve creep resistance by eliminating boundaries that can move relative to one another. The other part of this is that if we do have small grains in a material that's operated at high temperatures, as we know from recrystallization and grain growth, grains want to grow at those elevated temperatures. So they're going to naturally want to grow larger and larger. And so not only can there be slipping that occurs, but there can also be changing properties, right? So that could be cause differences from initial construction to later when these grains have grown. And so we don't typically like to see properties evolve over time, even if it's in a good direction. We want to know what the properties are going to be for the lifetime. So we typically want to start with those large grains in these applications. So those are just a couple of ways that we could resist this concept of creep, which is a high temperature, constant strain type of failure that occurs.